All right, ladies and gentlemen, hello. Welcome, welcome. All right, so I posted a Google Doc in the classroom. Please go there and follow along if you want. The purpose of this live stream is to offer up any questions and answer any questions you have about circuits. I know this is a pretty tough topic, and I'm sorry I couldn't be there, but yeah. So just let me know if you have any questions or anything like that. All right. So I want to start this off by, oh, okay. Oh, wait. No problem. How was everyone's day? Who is watching, that is? Oh, it says nobody's watching. All right. This is kind of a tough topic, so I want to make sure that we can take some time. You know, if he's asleep right now, if he gets up. All right. This is kind of a tough topic, so I want to make sure that we can take some time on questions you guys have. Go ahead and just add them to the Google Doc. We have editing, right? Yeah. I think everyone can access it. Wonder Wednesday. How's the baby's fine? Any questions about unit? Any questions about Unit 8 in particular? Did everyone? Any questions about Unit, the circuit packet? Can you guys hear me? Oh, I lagged. Okay, good. Maybe at the very end, but he's sleeping right now. I don't want to wake him up. What questions about circuits do we have? Series, parallel. Did everyone do the Edpuzzle? I mean, I can tell that. Thank you, Riley. Can I go over combo? Okay, yeah, absolutely. Combo circuits are the tough part because they involve both series and parallel. Just really quick summary. Can anybody tell me, just type in the Google Doc, what is true about a series circuit, or what is the difference between a series circuit from a parallel circuit? Just go ahead and type it in there. Yes, series current stays constant. Very good, Bridget. All right. For a series circuit, current stays constant. What stays constant in a parallel? What stays constant? Yeah, voltage. Very good. Okay. Yes, so those are the main differences. Now, with a combo circuit, however, it's really, there's no rules that are set for all the components in general, which makes it very complicated. So what you have to do is you have to take that complicated circuit and convert it and redraw it into a normal, basic, simple circuit, either all series or all parallel. And so I'm going to go over an example that shows just that, okay? Really quick, Claire, the reading quiz is going to be done in class. It's going to be a take-home quiz. I believe you should have a little bit of time on Friday maybe to work on that. I typed it up, and now I forgot everything that I typed up. So Mr. Borowitz will know the answer to that question. So Let's go ahead and let's actually, can everyone take out your circuit pack and go over flip to the very back, and we're going to go to number 1 on the back. Okay, I just want to go over that one. I think that's a pretty good example to start with. Okay. I'm going to draw it out here for you guys. Now, with that one, we have 4 resistors, all right? Some of which are in series, some of which are in parallel, and it's not really evident immediately how you can simplify this circuit down. All right, so we have this right here. I think it's over here. Okay. So we have a 15 volt battery hooked up to 4 resistors, R1, R2, R3, and R4. Now, really quickly looking here, you can definitely see that R2 and R3 are parallel, all right? Because, well, I mean, oh, they look parallel, but just because they are geometrically parallel does not mean that they are physically parallel, like through circuits, all right? The main reason why is that in physics, the term parallel means something different than what it means in geometry. Anybody who's taken any programming classes know that the term parallel actually means at the same time, like a parallel function will be running at the same time as one other line of code. And so, for example, R1 and R4 here are geometrically parallel, right? However, they are not in parallel with each other as per the circuit rules. The main way that you can tell whether they're in parallel or whether they're in series is you have to envision the electrons traveling through the component. All right. If you have an electron going through R1, it must go through R4. There's no other pathway for it to take. Whether it goes through R2 or R3 is separate, but it will always come back together and end up going through R4. Therefore, we say that R1 is in series with R4. Okay. Now, R2 and R3 are quite the opposite, right? R2, if an electron goes through R2, it cannot go through R3. You see that? Okay. Therefore, they're in parallel. Because the currents are going through them at the same time. Now, what's cool about that is that each of these will have the same voltage drop across from them, whereas the voltage drop over R4 and R1 would be different from each other, depending on their resistance. But no matter what, we have to combine some resistor. We have to simplify this circuit to make it easier to solve. I want to make this either all series or all parallel. And immediately, it might not become readily apparent just from looking at it. That's why on the on that Edpuzzle that we did, the guy was a little weird. He's like, just become one with the circuit, right? It doesn't always work like that. There's really no hard and fast rules, but in general, what I like to say is that if you have one component per branch, that should work out, that you can then combine them. So like, for example, R2 and R3, there are 2 different branches between what I call, or what, not what I call, but what people call nodes. Now, I know that we just talked about nodes in the last unit as it pertains to waves, but in circuits, a node is a spot where 3 or more wires come together. And as you can see, there are 2 pathways from this top node to the bottom node. Now, this pathway only has R2 on it. This pathway only has R3 on it. And therefore, since there's only one component on each of those pathways or each of those branches, we can squeeze them together and combine them to form one resistor. Okay? Right. So, like, for example, you could not combine R1 and R4 into one resistor in a similar manner, because if you look here, there's only one branch. Or if you really consider these 2 separate branches, there would be 3 on each branch, which wouldn't be nice, simple series circuit. Looking like this. R1, R4, what I'm calling R23. All right, R23. So now the subscripts I'm using are to kind of help me remember which resistors are equivalent to what. So essentially, by using the R23 subscript, I'm saying that R1, or I should say, sorry, I'm saying that R2 and R3 are equivalent. If I cut the wires right here at the nodes, and I replace this whole double branch setup with just a single resistor, the overall current, the overall circuit is the same. So we say that they are equivalent. That's why the worksheets were referring to things as equivalent resistance. It just means total resistance. So let me kind of explain how to solve this. Now, this uses those VERP boxes is what I call them. Voltage, current, resistance, power. Do you have to use them? No. But I really would encourage you to do that. I'll walk you through this first one together. And essentially, now that we've simplified the circuit down, we can just have a single box for this circuit. So let me show you what I mean. He's awake now, but I think mom's got it covered. So. All right, so we have VIRP, R1, R2, R3. Sorry. All right. So you're, yeah, I know he has a set of lungs on him. Okay, so do you see how I set up this box down here? So where we have R1, R2, 3, and R4. So that matches up with the series circuit. So all of the rules still apply of a series circuit apply to this circuit here because we've simplified this down now to just a single series circuit. All right. So, so we can go ahead and start plugging everything in. You need a pacifier? Okay, you got it? Okay, cool. All right. All right. Yeah, his name is Henry Robert Guttone. All right. Now I've forgotten everything I was doing. Right. So we can now go ahead and we can plug in what we know about this. But what we realize is that we don't know anything about R23. So what we're going to do is we're going to create a brand new box just for R2 and R3 combining together. All right, so I'm going to draw that off to the side here. So really, this problem has become not just a single box problem, but a two-box problem. Depending on the complexity of the circuit, you might have 2, 3, 4 box circuits. Again, you don't need to draw the boxes, but I think they're pretty darn helpful. All right. All right, so we got two boxes here. We have one box. Okay, one box right here. That's going to be for combining R2 and R3 into R23. And then we got a second box combining R1, R2, R4, and the total. Any questions on that? Okay, cool. Again, guys, if you have any questions at any time, just type them in the Google Doc. I have it open on my other monitor here. Okay. All right. So what we're going to do is we're going to go ahead and we're going to plug in everything we know into these two boxes, all of our givens. So we have an 8. Wait. Why? Oh. Why do we need tables? Okay, that's a great question. It's well, two reasons actually. The first reason, why do we need two tables? Why do we need two tables? Because you know, actually, I should have been more clear about that. That's a great question. We need two tables because there are rules for series and there are rules for parallel, but they're not rules for combo, right? For anything like this, there are no rules, all right? But we know rules for this. So we can use the fact that like in a series circuit, current is all constant. Well, this is a series circuit, so we can put current constant all through here. We know that this over here is a parallel circuit, and so all the parallel rules apply to this box. In fact, in that top left corner, I often like to put, I mean, you don't need to, I often like to put a P for parallel and an S for series, so we know what set of rules combine together. That makes sense? All right. So do we add the verb values for R2 or R3? How does it work for the chart where they combine? Okay, let me show you that. That's actually a good question. So let's start off by writing down everything we know, okay? If we have R2 is going to be 10, R3 is 40. All right, we know R1 is going to be 8, and R4 is going to be 12. All right, so we've now plugged in all of our resistances here. Okay. All right. Now you notice that in this box, I've left this blank, R2, 3, because we don't know exactly what it is. That's where this box comes into play. That's why we need this box, is in order to get what is the resistance for R2, 3. Oh, there's one last thing. We have 15 volts. Can anybody type in the Google Doc and tell me, where do we put that 15 volt? Yes, good job, Mitchell. Under total voltage. All right. So we're going to put that under here. A common misconception is that a lot of people put that right here under the R23. But we know that the voltage across that R23 is not 15 because the voltage across R23 plus the voltage across R1 plus the voltage across R4 add up to 15. So we cannot put 15 down here. Okay, that makes sense? Okay, so we can put it over here. All right, so now we have all our givens down here, everything we need to solve the circuit. So let's go ahead and let's just do it. Really, it may seem very complicated, have all these boxes, have everything else, but all it is just Ohm's law, V equals IR, okay? And if we can do that, we should be fine, right? So let's walk through it. The first thing is I want to go ahead and figure out what is the total resistance for R23. So we have 10 and we have 40, and immediately you might say, oh, well, it's just 50 when you combine them. However, you do not actually add them together directly. Again, we have to use that weird equation that 1 over RT equals 1 over R1 plus 1 over R2. All right, so you get 1 over 10 plus 1 over 40, all right? And that combines together to be, well, I'll let you guys go ahead and calculate it. Well, it looks like Mitchell's already got it. I was going to give the person who got it first a Snickers candy. So I think Mitchell kind of beat everyone to that. All right, so Mitchell, you've earned yourself a little Snickers, okay? Now, we get 8, right? 10 plus 40 equals 8, which is weird. You might be thinking, well, how is it that we get a lower resistance when we're adding in parallel? Right? Because in series, when you combine the resistors, you're increasing the resistance. You're getting more and more resistance. But in parallel, you get less. When you add a resistor in parallel, the overall resistance actually becomes less than the smallest resistor in the circuit. And the analogy I like to use with that kind of makes sense in my mind, is like in series. When you're adding resistors in series, you're adding more cars to a highway. You're increasing the traffic. You're increasing the resistance. When you add a resistor in parallel, you're opening up another lane. So the traffic goes down. And that's the idea with that. So that's why when you add in parallel, you actually decrease the overall voltage. Okay. So we have 10, 48 here. All right. So now it may be kind of weird because like we can't solve anything on this box. That's it for that box. We don't know the voltage. We don't know the current. We don't know the power. We can't do anything else with this box, but that's okay because we can come back to it later. For right now, we know that R23 is going to be 8. So over here in this box, we can go ahead and plug in 8. So now we have 8, 8, and 12. All right. And since this is in series, we can just directly add them. So we get a total resistance of 28. All right. And finally, we can use Ohm's law, which we know and love. V equals IR, V equals IR, and we can go ahead and solve for the current, which is just going to be 15 divided by 28. So we get 0.54. All right, 0.54. And so we can go ahead and use all of our rules now for series circuits here. So what is going to be the total, or I'm sorry, what is the rule with series circuit? What do we know about the current in a series circuit? Always stays the same. So that means that we can take that 0.54 and we can just roll it all the way up and we get 0.54, 0.54, 0.54 for every part in the circuit. All right. And so we get all of our other boxes filled out just using Ohm's law. All right. Oh, and don't forget, power is simply current times voltage. P equals IV. Okay. And so once you fill out this box, you can then take this row, this R, sorry, where are we at? This R23 row, and then connect it here because these two, R23 and R23, should be identical. So we're going to get anything in this row is going to be equal to that row. And from here, we can use all of our parallel rules in order to fill out the rest of this box. And so now finally, we know the voltage, the current, the resistance, and the power over every single component in that circuit. So when you have an instruction that just simply says solve the circuit, that just means solve for voltage, current, resistance, power for every component on the circuit. Now, as I'm sure everyone's guessed, this is very algebra heavy and very number crunchy, and the AP board's probably not going to ask you to just solve a circuit directly on the AP test. However, all of the rules in going through this will get you more familiar with the rules for parallel, the rules for series. So that way, when you are, say, writing a paragraph about a circuit, you can use those rules to justify any answers you have. So this is really to help you become very familiar with the rules of parallel and series and combo circuits. Okay. Are there any questions on that? I pushed the due date for the circuit packet back until Friday. So I think it was technically for yesterday or something, or Monday. So if you want to submit that a little bit later, you can do that just fine. Reading quiz should be at the end of the week, and the actual test is going to be next Tuesday. Oh, how do we submit the picture? Yeah, you can take a picture of it. You can give it to Mr. Borowitz, and he'll collect it that way. That's fine too. But yeah. Any other questions? What if you are missing Friday? You can hand it in early. If you're absent on Friday and want to hand it on Monday, that's okay. If you are present Friday and hand it on Monday, that's a different story. A live Wonder Wednesday. Okay. What? I can make it quick. I want to make sure you have time to work. What is? I gotta be going pretty soon here. But you gotta have the quiz. The quiz. Oh, for the quiz. Oh, shoot. Okay, hold on. Let me see. That's actually a really good question. I wrote it down here. Hold on a second. All right. So for the reading quiz, right. So it's gonna be a take-home reading quiz. So you're gonna get it on Thursday, and I was going to collect it on Friday, but again, if you're absent on Friday, I'll just collect it on Monday. Okay. Or, you know what? Actually, no. If you're absent on Friday, take a picture of the reading quiz and submit it to the Google Classroom or email it to me or something like that. Okay, but don't. But since it is going to be a quiz, I want you to submit it before the end of the day Friday. So by midnight on Friday. Okay. If you're not here Thursday, that is that Jack. Jack, are you not going to be here Thursday? Are you just like never in school? All right. Okay, Jack will be here. Good. If you're not here Thursday, talk to Mr. Borowitz. He can give you a copy. I should have some hard copies already printed out in the room. If not, I don't want to put him on the spot. Sorry. If he doesn't have any hard copies, just let me know. I can send you a PDF copy. You can print it off at home. Wonder Wednesday, we wonder what baby looks like. Of course. Oh, wow. It's bold and like 72 font. Who's not going to be here on Thursday? No, it's me. Okay, thanks. Okay. All right. Really quick, sure, fine. Are there any other questions about circuits? Anything else that you guys have? You guys are so creepy. Jesus. Okay. I'll be right back. He's asleep, so he might be angry if I pick him up. Will be okay? Oh, you changed nothing? Did you change his diaper? All right, this is Henry. There you go. All right. Hold on. He's sleeping, but there he is. Okay. See, there you go. It's all right. Any other questions? Just let me know. And I'll have the Google Doc open. I'm going to end the stream for right now, but I'll be answering any questions you have in the Google Doc as you're working through the circuit packet. I know you guys got doubles today, so weird. Okay, have a good one, guys, and I'll see you all on Monday.